Swayam Prabha. Digital India. Educated India.
Hi friends, now we will discuss on the topic energy production from biomass and waste. Already we have seen that biomass is one of the most important resource for renewable energy production, and this biomass can be used as a fresh biomass or the waste biomass like say agricultural residues, forest residues etc. And this biomass and waste can be processed in different routes like say thermal route, chemical route and biological route, and physical routes can also be used for the preparation or pre-treatment or for to make the biomass suitable for use in a particular type of reactor. Now, all of us we know that the coal is produced from biomass, plant biomass basically. So, the technologies or the processes which we have discussed for the conversion of coal to energy, those can also be applicable in case of biomass, but in this case as you know the volatile matter is higher in case of biomass. So, the requirement of reaction conditions will be milder than that of the coal conversion. Now, if we see that biomass is having more volatiles, so apart from thermal combustion route, thermal processes like combustion, gasification, pyrolysis etc., we can use biological routes also for the conversion of energy from it, particularly when we will consider the waste biomass and organic part of the municipal solid waste. So, municipal solid waste contains good amount of organic part that contains high amount of carbon as well as moisture content is also high. So, that part can be converted to biogasification routes, and some of the waste contains lipid containing materials, high amount of lipid is available in it. For example, say oil seeds to oil. So, vegetable oil and oil from non-edible oils, edible and non-edible oils both can be converted to biodiesel through the chemical route, or say waste cooking oil that can also be converted to biodiesel through chemical route. And as you know the biomass is highly reactive than coal and its density is less. So, to use this biomass in a particular reactor to give the sufficient strength and to maintain the particle size, the densification of the biomass and waste is required. So, we will discuss all those things, but we will not cover the thermal conversion routes because we have already discussed these things in these processes in case of coal conversion. So, similar concept will be applicable for biomass also for its conversion to electricity or other fuels. For this class the contents are biomass and waste as a source of energy, then biomass and waste to energy conversion routes, and then anaerobic digestion of biomass and wastes. We see here this slide shows us some biomass residues, grass, corn stover and bagasse and wood chips. So, these are the agricultural waste, and we see in these agricultural waste which contains cellulose, hemicellulose, lignin and others. So, good amount of cellulose and hemicellulose is available, lignin also we have significant amount. So, this is the structure of a lignocellulosic biomass. So, we have lignin outer part, then we had cellulose mostly structured, and then hemicellulose not that structure one. So, these three components are available in biomass and the biomass residues or waste biomass. So, this can be a source of energy, and if we see the municipal solid waste. So, different part of the municipal solid waste or components of the MSW are provided here. So, paper, cardboard bags, wood carrots, boxes, scraps, and bush branches, leaves, grass, garbage, green stuff, grains, rags, etc. So, you see here in these out of these components, somewhere we have moisture 5, somewhere we have moisture 75%. So, as we have discussed that low moisture content will be processed through thermal route and high moisture content will process through biological route, and these biological routes we will be discussing now, and we see here all the cases we get some heating value. So, it is very clear from this that we can recover this heat which is available in the waste and biomass for energy production. Now, we will see the different routes which can be used for the production of energy from the biomass and waste. So, if we have biomass and waste, we can use it through thermochemical conversion like say combustion, gasification, pyrolysis and liquefations, the similar to coal. So, we are not covering this part, and then biological conversion we can use for the use of this biomass and waste and its conversion to energy. So, those important routes, biological routes are anaerobic digestion which gives us methane, that is biogas, and then fermentation can give us ethanol or higher alcohol, and some enzymatic routes again the ethanol and amino acid they can give it. And we will be concentrating in this class on anaerobic digestion. So, this is a commercial process and the fermentation is under development particularly for the waste materials, and then chemical conversion, another method we have, that is hydrolysis, solvent extraction and transesterification. We will be giving more focus on transesterifications in the next class, and then physical conversions is also required, as I have mentioned that to make the feedstock suitable for its use in a reactor system. So, then these are say densification or briquetting, and then other physical methods, mechanical extractions and distillation. We will discuss these 3 routes consecutively. Now, we will see the anaerobic digestion of biomass and waste. So, all type of waste and biomass may not be suitably converted through anaerobic processes, but certain waste and biomass can be processed easily and most economically also you can say can be converted. So, some examples of those food feedstocks here are energy crops, animal waste, industrial waste, MSW, some part of it, and then restaurant and food industry waste and sludge from wastewater treatment plant. So, all those things are the feedstocks for the anaerobic digestion process, and this anaerobic digestion process is a complex process, a series of biological processes in which microorganisms break down biodegradable material in the absence of oxygen. So, anaerobic condition is required for this process, and then it gives us biogas, it can give us hydrogen, it can give us biofertilizer, compost, and we can also get some water from the slurry after proper treatment. Now, we will see the mechanism or different types of phenomena which takes place during the production of biogas or methane in the anaerobic digester. So, we have complex organic compounds, carbohydrate, fats and proteins available in our feedstocks. Then the first step is the hydrolysis. So, after hydrolysis we will get simple organic compounds, that is sugar, amino acids and peptides. So, those are the our preliminary feedstocks for biological reactions. So far we have hydrolysis, and then it will be having some fermentation also, and then these sugars can be converted to short chain fatty acids through the acidogenesis route, and some microbes are available to convert it to hydrogen, some microbes also convert it to acetic acid, and this acidogenesis microorganism. So, this simple sugar will be converted to short chain fatty acids, then short chain fatty acids will be converted to acetic acid through acidogenesis. So, this is acidogenesis, that is simple organic compounds to short chain fatty acids, and this is acetogenesis, that is short chain fatty acids to acetic acid or acetate. So, this can be either this way, or some microbes also produce hydrogen, then that hydrogen and CO2 that also be converted to this. So, both type of a complex biological reactions are going on in the AD or anaerobic digester. Then the acetic acid which is formed, that is further converted to methane through methanogenesis. Some microbes are responsible for this conversion, and this H2 and CO2 which is available in the media, those can also be converted to CH4 and CO2 can also be produced, and this is called methane producing bacteria. So, this is the overall reactions which reaction scheme which takes place in the anaerobic digester. Now, we will see the relative contribution of different type of processes. So, if we have organic compounds here, then short chain fatty acids we can get around 76% of that, and then short chain fatty acid directly acetic acid we can get 20%, directly hydrogen we can get 4%, and the major process is your through this short chain fatty acid production. The first step, major step, is the conversion of organic compounds to short chain fatty acids through hydrolysis and then acetogenesis. Then these fatty acids will be converted to acetate mostly, and some part is hydrogen. So, around 52% and 24%, this is the relative abundance of different types of processes, and then acetic acid to methane and then hydrogen to this. So, out of total methane, so 72% is coming through this route and around 28% is coming through this route. So, this is the major reactions, hydrolysis and acetogenesis, then acetogenesis and dehydrogenation, and then methanogenesis. So, these are the basic reactions which take place in the anaerobic digester. Now, how we can represent this formula? This is a complex process. So, like unlike say coal combustions or gasification, we cannot represent very simple formula here. So, this is a complex one, and then people tried to represent in terms of chemical expressions, and empirical relationship have been proposed. As one example as available in this and proposed by this researcher, you see C and HAOBNC reacts with this amount of oxygen, this many moles of H2O, and gives this one. Actually, there are some microbes. So, microbes are there, they take in water and then react on this and then gives the product CH4, CO2, HCO3, NH4, and this is, and these organic compounds is taken up by the microorganisms and they are biomass growths. So, this is the biomass C5H7O2N, the cell biomass growth. So, this is the empirical relationship. Now, we can get the value of N, A, B and C on the basis of elemental composition of the feedstock, and then we have to know S and E, then all the coefficients we can know. So, what is S and E? We see here, S is the fraction of waste converted into cells. So, how much waste we are taking here, that will be, if we take the mass balance, then it will be partially converted to the cell biomass and remaining part will be converted to the energy. So, that is why S equal to fraction of waste converted into cells, then E equal to fraction of waste converted into methane or energy. So, S plus E is equal to 1. So, now by mass balance we can get the value of S and E, and we can put this expression, we can predict what can be the biogas formation in this particular feedstock and in this process. And this C5H7O2N is the empirical formula for bacterial biomass, and CNAN is the empirical formula of the waste being digested. Now, we will see different type of bacteria which are responsible for this anaerobic digestion processes. So, hydrolysis or hydrolyzing and fermenting bacteria. So, hydrolysis takes place and then fermentation also takes place. So, here what we get, hydrolysis product sugar, then alcohols, then amino acids and glycerol. So, they will be further converted to different compounds in the acetogenesis phase. So, acetogenesis phase sugar is converted to fatty acids, then alcohols to fatty acids CO2, and ammonia is also fatty acids and glycerol acetate. So, these are the different products which are produced through this acetogenesis step. Some example of these bacteria are also given here, that is bacteroids and bifidobacterium, Butyrovibrio, Eubacterium and lactobacillus. Those act as acetogenic bacteria. E. coli is also helps in this process. Now, we will see the acetogenic bacteria. So, acetogenic bacteria, that is Clostridia and Acetivibrio are some example of acetogenic bacteria. So, these bacteria converts to acetic acid, this is the fatty acids to acetic acid conversion. So, acetogenic bacteria, and then these are the presentation of propionate to acetate, propanol to acetate, butyrate to acetate, and then homoacetogens are also available. Those convert H2 plus CO2 to acetic acid. Just we have, if you see the this one, this conversions homoacetogens, and hydrogen producing acetogens are also these reactions. Now, methanogenic bacteria. So, some bacteria are there which helps the methane formation reactions, and these are basically two types. One is acetoclastic methanogens. So, acetoclastic methanogens means acetic acid will be converted to methane by these microorganisms, and another is your hydrogenotropic methanogens. Hydrogenotropic methanogens means hydrogen plus carbon dioxide will be converted to methane plus to H2O. So, if we see out of these two routes, that means here this says to this route and this route, the contribution here is around 70% and here it is around 30%. So, now the formic acid and methanol if present in the media, then those can also be converted to methane as per the formula HCOH CH4 plus 3 CO2 plus twice H2O, and this is the for methanol to methane conversion. These methanogenic bacteria have been classified into different groups depending upon their 16S ribosomal RNA fingerprinting, and group 1, group 2 and group 3 are some examples are given here, and these bacteria are unicellular, these are gram variable, strict anaerobes and do not form endospores. So, these are the some basics of the microorganisms which have been used for the anaerobic digestion process. Now, we will see how we can perform the anaerobic digestion reactions, or how we can process the feedstocks, that is the waste and biomass to produce biogas. So, obviously the reactor or microorganisms will react on certain types of molecules. So, initially what feedstocks we are having in terms of waste, that has to be converted to the initial compound which will be degraded by the microorganism. So, some pretreatment is required, and also we have to get the size reduction etc. from the original feedstock. So, if we have organic feed, then water and chemicals, then there will be some shredding, blending and pH adjustment, which is the pre-requirement for the growth of bacteria and the conversions of the molecules from the higher molecular weight to the lower molecular weight and finally to methane. And then we need the pretreatment of feed. This is basically very useful when we will consider for lignocellulosic biomass, because lignin is not biodegradable. So, we have to separate the lignin part from the biomass, and then the non-lignin part will be used for further processing. So, this is pretreatment is required. Then after pretreatment, removing the undesirable materials in this and making the feedstock more suitable for biological conversion, it is going for anaerobic digestion. So, this in anaerobic digestion we maintain mesophilic or thermophilic condition. So, at this temperature around say 35-40 degree centigrade temperature, the biogas is formed, and then this biogas goes up from the digester, and this biogas can have some impurities. So, we need to remove the impurities, and we need mixed gas separation. Then water, acid gases and organosilicon mostly available. So, we need to purify this gas and we can get the methane, or that is called synthetic natural gas or biogas. Then the slurry part which we are getting here, so that will go for dewatering step, and dewatering step will give us some sludge and some liquid. So, liquid will be treated further for the production of water, and the sludge which we are getting, that sludge will be used for other purposes, maybe say composting or as a fertilizer, etc. And this part of this sludge recycling is required to maintain the microbial biomass in the anaerobic digester. So, this is the overall flow sheet of the anaerobic digestion process. Now, we will see the type of anaerobic digestion process. So, initially anaerobic digestion process was used with a substrate concentration of around 8 to 10%, and that is the wet state of anaerobic digestion. Now, gradually people developed some improved version of this, and that is called dry anaerobic digestion, and we see the difference between these two wet and dry anaerobic digestion processes in this table. So, we have some processing mode, and then we will compare those, that is total solids content, and then we see dry, as you have mentioned, that is 25 to 45% solid may be available, whereas this is 8 to 10%, and here it is mentioned that 2 to 15% for wet process. And so, once the moisture is more, water is more, so obviously the reactor volume will be higher in case of wet process, and dry process the volume will be less. And solid liquid separation, again dry will be simple, and this will be expensive because more liquid is available here. And energy balance, this is more improved for dry and less improved for the wet process, and economic performance more improved for dry than the wet process, and retention time also here shorter than the wet process, and type of feedstock accepted, that is greater flexibility we have for dry process, but wet process we have lesser flexibility. So, this is the development of the wet process in last few years, and we will see now the kinetics of the methane productions. So, we have seen that there are number of steps. So, as the overall kinetics of the biogas production, obviously any one step, which one will be the lowest step, that will control the overall kinetics. So, basically in normal cases the methane production step is very slowest steps, and then that controls the overall kinetics of the AD process. But depending upon the feedstocks, the other steps may also be responsible to govern the overall kinetics of this. Like say if lignin is very high, then obviously the biological conversions will be less, and the hydrolysis will also be slow, and that will be the rate limiting step. And in cellulose content is high, if the cellulose content is high in feedstock, then hydrolysis may be rate limiting step. Somewhere gas transfer can also be limiting the process. Now, overall rate kinetics if you want to represent, so R is equal to SO into mu max theta minus 1 minus Ks by theta into mu max theta minus 1. So, here SO is the substrate concentration in the feed, mu max is the maximum specific growth rate, and theta is the residence time. So, Ks is the saturation constant or substrate concentration at which the specific growth rate is half of mu max. So, that way we can get the value of R, that is the substrate converted per liquid volume at hydraulic retention time of theta. So, this theta value hydraulic retention time, that will be dependent upon the nature of materials we are using. So, you see here at 30 to 37 degree centigrade, optimum conversion of glucose can be achieved at theta of 4 hour for acidogenic phase and 4 days in methane phase reactors. But if we use other say cellulose, then this theta value will be increased. So, that was 4 hour, but in this for glucose, but now here we are 1 to 2 days for acidogenic phase, and which was 4 days, and then it is 5 to 8 days for methanogenic phase. And this table shows us some mu max and Ks value for different types of compounds, the glucose, cellulose, and for acidogenic phase and also for methanogenesis phase. Now, there are some important facts regarding the anaerobic digestion of biomass and waste. In the digester, if we maintain high temperature, we will get more production of biogas, lower the temperature, lesser the biogas production. So, in the country where the temperature is very less, at the time some heating arrangement is made, making some jacketed vessels like this. So, some heat or steam or some other fluid is sent through it, hot fluid is sent through it to maintain the temperature, and pressure has not much significant effect on it. Reduced pressure also provides little or no benefit, and then low pH and short retention time precludes growth of methanogenic bacteria. If pH is very low, then methanogenic bacteria will not grow, and retention time is also less. So, complete conversion will not be possible, and here we do not need a very vigorous stirring. We need rapid continuous agitation of anaerobic digester is not necessary, and in some cases it is even harmful. And specific methane yield, so how much methane will be produced per unit mass of substrate, that will depend upon the volatile matter content in it, that is how much biodegradable COD or VS loading in this. So, these are the some important facts related to anaerobic digestion reactions, and now we will see types of anaerobic digesters. There are two types of digesters, one is low rate and another is high rate. So, low rate means retention time will be higher and high rate means retention time will be lower. So, here for low rate retention time is 30 to 60 days, whereas for high rate it is retention time is less than 15 days, and so feed rate will also be lower in case of low rate and higher in case of high rate. Here you see 0.5 to 1.5 kg volatile solid per meter cube per day, and then we are getting 1.6 to 6.8 kg and volatile solid per meter cube per day. So, this is the difference between these two types of anaerobic digesters, and most digesters are heated and operated in the mesophilic range and usually made of concrete and steel as a material of construction. And then what will be the digester operation? Obviously, it handles the microorganism, so certain pH should be maintained. So, pH is microbial growth is very specific to pH. So, optimum pH is 7 to 7.0, and most digester operates in the temperature of 30 to 38 degree centigrade. And what we see the pH, how can we maintain the pH? We can add some alkali if needed, or we can by properly seeding fresh added sludge and not excessively withdrawing sludge. If we do not withdraw excess sludge and we do not add very high amount of fresh sludge, if we can maintain certain ratio, then the pH can be adjusted, because pH changes can take place during the reaction. And then heavy metals may inhibit digestion process and must be eliminated at the source. The pretreatment and heavy metal removal will be done at the earlier stage, and then the supernatant liquid which is generated here, that also contains some amount of organic, that can be biodegradable organics. So, those can be treated and clean water can be produced. Now, we will see the development in the anaerobic digestion processes and the anaerobic digester we will see. So, we have come to know that anaerobic digestion process takes through two important routes, one is acetogenic and another is your methanogenic routes. So, acetogenesis takes place at lower pH and methanogenesis takes place at higher pH. The pH range is given here, say 5.5 to 5.9 for acetogenesis, and then for methanogenesis 7.4 to 7.9, or we are maintaining here pH around 7. So, both microorganisms are not able to give us their maximum performance. So, if we can use two reactors in place of one is at this acidic range and another is at basic pH, as mentioned here. So, the microorganisms can give us their best performance and our overall efficiency can be improved. So, that is the concept for use of two stage digester, and we see here sludge in we are using here or the feedstock here, then we are mixing zone and actively digested sludge, then gas out, then it is sludge out the first step, and then it is a mixed liquor is coming out from the acidic zone, acidic pH is this one, then this is coming here and it is coming to after pH adjustment, say we are going through methanogenesis steps and we are getting gas, and we are getting supernatant the liquid part and then the sludge. So, that way we can use two step AD process in place of one. So, we will get better performance of the process. So, up to this in this class, thank you very much for your patience.